Linear Algebra, Lecture 6. We started to talk about matrices last week. We will be studying matrices forever. So an M by N matrix is just a rectangular array of numbers, of scalars, M rows, N columns. That's what the M and N mean. And the coordinate in row I, column J, has subscripts. This is the standard notation. IJ in that order. So if you have your matrix A, this is the first row. This is the ith row. All the way down to the last row, which is the mth row. And again, you should be following in the notes because the notes are legible and my handwriting never is. This is row I. This is column J. So if your matrix were 1, 2, 3, 4, 5, 6, then, and if Aij is the coordinate in the ith row, jth column, using our standard notation, for example, A23 would be the coordinate in the second row, third column, which is 6. A12 would be the coordinate in the first row, second column, which is 2. A21 would be the coordinate in the second row, first column, which is 4. Okay. Any questions about that? And you can add and subtract matrices of the same shape. So if A, this is our standard notation, Aij, and B, Bij are both M by N matrices. If we write A plus B is the matrix C, where the coordinates are Cij, then the ijth coordinate of C is just the sum of the ijth coordinates of A and B. So for example, if A is 1, 7, minus 3, 0, 2, 11, and B is 3, 9, minus 1, 5, 0. So these are both 2 by 3 matrices. Same number of rows, same number of columns, so you can add. So if A plus B is the matrix C, what are the coordinates? Well, first row, first column, 1, 3, you add, you get 4. First row, second column, 7 plus 9 is 16. First row, third column, minus 3 minus 1 is minus 4, and so forth. You add the first, second row to the second row, you get minus 1, 7, 11. That's the sum of the matrices. Okay. Any questions about that? And you can also multiply a matrix by a scalar, lambda times A, lambda is some scalar, or lambda times Aij. It shows the matrix you get by multiplying every coordinate by the scalar. So for example, what is 5A in this example? So that's 5 times the matrix, 1, 7, minus 3, 0, 2, 11. You multiply everything by 5, you get 5, 35, minus 15, 0, 10, 55. So this is scalar multiplication of a matrix. So just to make sure you,
So can I see that page one more time?
sure.
Okay.
Just to make sure you can do these calculations. Suppose A is the matrix 7, 1, minus 3, 0. B is the matrix 2, 5, minus 1, minus 4. So do the following calculations. A plus B, A minus B, 6A, 6A minus 3B. So these are all going to be 2 by 2 matrices. Matrices must have the same shape to add or subtract them. So do these calculations, and we'll pause for a minute, and I'll pause for a minute and give you a chance. Okay. Can someone tell me what is the matrix A plus B? When you add the two matrices together, what do you get?
Nine, 6, -4, -9.
7 plus 2 is 9. 1 plus 5 is 6. Minus 3 minus 1 is minus 4. 0 minus, what is that, a 4? Minus 4, yeah. Any questions about that? What is A minus B?
Oh, I thought we was doing row and column. Like what we did last time.
What do you mean? This is, we're adding the matrices, so you add coordinates.
So you don't do row, the rows and the column?
I don't know what you mean by that. I mean, you add the rows, you add the columns if you like, but this is matrix addition. You add, just as I did in the, right here, this previous problem, A and B. So A plus B, first coordinate, 1 plus 3 is 4. You add the
Okay.
numbers in the proper places. So I'm
Okay.
adding these matrices. 7 and 2 is 9. This is addition, right? It's a plus sign. You might be thinking about matrix multiplication, but there's no multiplication on this page yet.
Okay.
When you take the matrix A minus B, what do you get? What is the first row? 7 minus 2,
5.
5. 1 minus 5, minus 4.
That's 4.
Minus 3, minus 1, minus 2. 0 minus 4 is plus 4. Take the matrix A, multiply it by the scalar 6. What do you get? What's the first row?
6 times 7 is 36. No.
So the first row, you take, multiply everything by 6. 6 times 7 is 42. 6 times 1 is 6. 6 times minus 3 is minus 18. 6 times 0 is 0. Okay. What's 6A minus 3B? This is 6A. What is 3B? 3B, if I multiply this matrix by 3, that means multiply every coordinate by 3. I get 6, 15, minus 3, minus 12. 6A minus 3B, 42 minus 6 is 36. 6 minus 15 is minus 9. Minus 18 plus 3 is minus 15. 0 plus 12 is 12. So this is matrix addition and matrix multiplication. Okay. Right, any questions about this? Okay. So next, we talked about matrix multiplication. And matrix multiplication is a little bit trickier. So suppose A is an m by n matrix. Now, unless the matrices are square, you cannot multiply matrices that have the same shape. You can multiply matrices A and B if A is an m by n matrix, so the matrix A has m rows and n columns, the matrix B has to be an n by p matrix. All this means is, this is the important thing, that in A, there are n columns. In B, there are n rows. The m and the p can be any integers at all, so long as the number of rows, the number of columns in the matrix A equals the number of rows in the matrix B, you can multiply them. The simplest case is when you have a row. So a row, this is an 1 by n matrix. One row, n columns. And B is an n by 1 matrix. B11 means n rows, but just one column. You can multiply a row and a column when they have the same number of elements, and you just multiply coordinates and add. So let's just make it, it's easier if I just give an example. Suppose I have 1, 2, 3, 4, 5, 6. A row times a column, 3 numbers, 3 numbers. So I multiply the 1 and the 4. I multiply the 2 and the 5. I multiply the 3 and the 6, and I add. So that's 4 plus 10 plus 18, which I think is 32. Right? This is how you multiply a row times a column. Let's take another example. 2, 0, minus 1, 11. 5, 19, minus 2, minus 3. So if you multiply this row by this column, you get a number. And what is the number? 2 times 5 is 10. 0 times 19 is 0. Minus 1 times minus 2 is 2. 11 times minus 3 is minus 33. So 12 minus 33 is 21. Right? This is also, if you took a vector calculus, this is what was called the dot product of two vectors, or the scalar product, or sometimes the inner product.
Wait, so can you multiply the two vectors if m equals p, or does that only work for m1 by n vectors?
No. So this is 1 by n. This guy is n by 1. In this case, if these are going to be vectors, there's going to be just one row and one column. So m is 1 and p is 1. But this is the rule. You can multiply m by n and n by p. M and p can be absolutely anything, but these two numbers have to be the same.
Okay, but M and P can equal each other.
Okay, yeah, so long as, yeah, it doesn't matter, it makes no difference. M and P can be anything, right? So in the simplest sort of non-trivial case, let's say you have M equals N equals P equals 2. So you're multiplying 2 by 2 matrices. Right, but I haven't explained yet how to multiply matrices, or at least I haven't explained today. I'll do it right now. The way you multiply, so suppose you have, this is an M by N matrix, and this is an N by P matrix. And the result is going to be an M by, so this is M by N, this is N by P, this is going to be M by P. It's almost as if the N's cancel. And in this matrix, let's call this A, B, C. What is the ijth component of this matrix? This is in the ith row, jth column coordinate. So the way you get the ijth component of the product is you take the ith row, this is row I in A, and the jth column in B, and you multiply them. The ith row will have coordinates AI1 up to AIN. Because this is an M by N matrix, it has N columns. So in the ith row, there are N numbers, one in each column. The matrix B, its jth column, will have coordinates B1J down to BNJ. This matrix has N rows. So in the jth column, there's one number in each row, there are N numbers. So Cij will be what you get when you multiply this row times this column. It will be AI1, AB1J plus AI2, B2J up to AIN, BNJ. Or using sigma notation, this is summation AIK, BKJ, where K goes from 1 up to N. So you should memorize this formula. This is the formula for matrix multiplication. And you need to know how to do this in practice. So what was the example I wrote down a moment ago? Let me see where I lost it. I'll just write down another example. Suppose I take the case, 2 by 2 case. So suppose I take a matrix, I don't know, 1, 2, 3, 4, and a matrix 5, 6, 7, 8. So the important thing is the number of columns here equals the number of rows here. The fact that the number of rows equals the number of columns is irrelevant. It's not good nor bad. It doesn't matter. But this is a 2 by 2 matrix. This is a 2 by 2 matrix. So the result will be a 2 by 2 matrix. The inner twos cancel, but it's still 2 by 2. So there's what goes into the first row, first column of the product. You take the first row times the first column. 1 times 5 plus 2 times 7 is 19. For the second row, first column, you take the second row into the first times the first column. 15 plus 28 is 43. Second row, first row, second column, first row times the second column. 6 plus 16 is 22. Second row, second column, 18 plus 32 is 50. So the product of these two matrices is this. So what you should do is spend a minute and just carry out this calculation and make sure you get the same result. Any questions about this? How you get this? You really need to spend a lot of time learning how to do these matrix multiplication calculations by hand. Let's actually do another matrix multiplication. Let's multiply these same two matrices, but in the opposite order. I take the matrix 5, 6, 7, 8 times the matrix 1, 2, 3, 4. What do I get? If I multiply the first row into the first column, I get 5 plus 18 is 23. If I multiply the second row into the first column, I get 7 plus 24 is 31. If I multiply the first row into the second column, I get 10 plus 24 is 34. Second row times second column, 14 plus 32 is 46. So I get these two matrices. And if you look, you see this matrix and this matrix are completely different. If this were A and this were B, this is the matrix AB. This is B, this is A, this is the matrix BA. They don't look anything alike. So that's one of the most important facts about matrix multiplication. It's not commutative. So let me just write down. This. Matrix multiplication is not commutative. In general, A times B is not equal to B times A when they are defined. May happen, but not usually. So in general, AB is different from BA. It may happen that AB equals BA, but in general, that's not going to be the case. In fact, it's very interesting that, well, actually, it's suppose A is an n by n matrix. That means the number of rows equals the number of columns. So the shape is actually a square. It's what's called a square matrix. So A times A is also an n by n matrix, which we'll call A squared. And will that A cubed be A times A times A, or A squared times A, or A times A squared? And in general, A to the K will be what you get by multiplying A by itself K times. And this is always going to be an n by n matrix. So for example, if A is 1, 2, 3, 4, A squared, you multiply A by itself. So multiply A by A and tell me what you get. Let's see. First row, first coordinate, 1 plus 6 is 7. First row, second coordinate, 2 plus 8 is 10. Second row, first coordinate, 3 plus 12 is 15. Second row, second coordinate, 6 plus 16 is 22. What's A cubed? A cubed is A times A squared. A is 1, 2, 3, 4. A squared is 7, 10, 15, 22. So when you multiply, you get 7 plus 30 is 37. 10 plus 44 is 54. 21 plus 60 is 81. 30 plus 88 is 112. So this is A cubed. And so on. What about A to the fourth? You can get A to the fourth in several different ways. You can multiply A times A cubed, or you can multiply A squared times A squared. And matrix multiplication is not commutative, but it is associative. So these should always give you the same thing. Any questions about this? Now, once you can take powers of a square matrix, you can actually define matrix polynomials. So suppose you had a polynomial that say P of t is 2t squared minus t plus 1. I should say that the n by n identity matrix I sub n is an n by n matrix with ones down this main diagonal and zeros everywhere else. This is the 4 by 4 identity matrix. In general, if A is an m by n matrix, I can multiply A on the right by the identity in, and that's going to be A. And I can multiply A on the left by the m by m identity, and that's also going to be A. So this n by n identity matrix is sort of equivalent to the number 1. It's the multiplicative identity. The identity I times any matrix, for which the multiplication is defined, just doesn't change the matrix at all. So if I take a polynomial like P of t equals 2t squared minus t plus 1, if A is a square matrix, A is n by n, then I can define P of A, just plug in A for t, 2a squared minus A, and 1 you replace with the identity, plus I sub n. So for example, if A is 1, 2, 3, 4, and A squared, I calculated a moment ago, A squared is 7, 10, 15, 22, then P of A, which is 2a squared minus A plus the identity, that's 2 times the matrix 7, 10, 15, 22, minus A, 1, 2, 3, 4, plus the 2 by 2 identity, 1, 0, 0, 1. So this is 14, 20, 30, 44, minus 1, 2, 3, 4, plus 1, 0, 0, 1. So 14 minus 1 is 13, plus 1 is 14. 20 minus 2 is 18, plus 0 is 18. 30 minus 3 is 27, plus 0 is 27. 44 minus 4 is 40, plus 1 is 41. So if I take the polynomial P of t equals 2t squared minus t plus 1, and I plug in A for t, and I do my calculation, this is the result. Any questions so far? I should just add one thing about the identity matrix, because there is a function that's very useful in linear algebra. It's called the Kronecker. Kronecker was a mathematician in the 19th century. The Kronecker delta, delta sub ij. This is defined to be 1 if I equals j, and 0 if I is different from j. So for example, delta 1, 1 and delta 2, 2 are both equal to 1, because 1 is 1 and 2 is 2. And delta 1, 0 and delta, actually maybe I'll write this, delta 0, 0. Delta 1, 0 and delta 0, 1 are both 0, because these subscripts are different. So for example, the 2 by 2 identity matrix 1, 0, 0, 1 can also be written as delta 1, 1, delta, actually I should have kept it, delta 1, 1, delta 2, 2. So delta 1, 1 and delta 2, 2 are both 1, because the subscripts are the same. Delta 1, 2 and delta 2, 1 are 0, because the subscripts are different. So this is delta 1, 1, delta 2, 1, 2, delta 2, 1, delta 2, 2. So you can write the identity matrix, you can write its coordinates as the Kronecker delta. The ijth coordinate of the identity matrix is the ijth Kronecker delta, delta sub ij. Again, this just means if you're going down the main diagonal, the subscripts are the same, and this is a 1, off of the main diagonal of the matrix, the subscripts are different, then this is a 0. Let me just add a few other things. This is all basic matrix theory. The n by n matrix A is said to be invertible if there is an n by n matrix B such that AB equals BA equals the identity. So not every matrix is invertible, but if we take a matrix like, suppose I take A to be 3, 5, 4, 7. And I'm going to take the matrix B to be 7 minus 5 minus 4, 3. So I claim B is the inverse of A. Why is that? Well, I have to do the calculation. AB is 3, 5, 4, 7. 7 minus 5 minus 4, 3. So this is 21 minus 20 is 1. Minus 15 plus 15 is 0. 28 minus 28 is 0. Minus 20 plus 21 is 1. That's the identity. And if I did the multiplication in the opposite order, B times A, 7 minus 5 minus 4, 3, 3, 5, 4, 7. This is 21 minus 20, 35 minus 35, minus 12 plus 12, minus 20 plus 21. This is the identity again. So this matrix A is invertible, and this is its inverse, which we usually write as A to the power minus 1. Or if you like, this matrix is invertible, and this is its inverse. So this is also the same as B to the power minus 1. So this is really just a definition. And there's another operation on matrices, which is called the transpose. Transpose. So this is the operation where you interchange rows and columns. So if you have the matrix 1, 2, 3, 4, 5, 6, the transpose of that, I'll put a superscript T, means take every row and make it into the corresponding column. So in this matrix, the first row is 1, 2, 3. So in the new matrix, the first column will be 1, 2, 3. In this matrix, the second row is 4, 5, 6. So in this matrix, the second column is 4, 5, 6. So here I transpose rows into columns. Of course, I could also have transposed columns into rows. Here the first row is 1, 4. So here the first column is 1, 4. So here the first row is 1, 4. Here the second column is 2, 5. Here the second row is 2, 5. Here the third column is 3, 6. Here the third row is 3, 6. So you transpose a matrix by interchanging the rows and columns. This started off as a 2 by 3 matrix, and the transpose is a 3 by 2 matrix. In general, the transpose of an m by n matrix is an n by m matrix. So for example, and of course, if m equals n, then the transpose doesn't change the shape. If I have the matrix 7 minus 2, 3, 0, what is the transpose of that? Can someone tell me what will be the first column of the transpose? The first column of the transpose is the first row of the original matrix. So if the first row is 7 minus 2, the transpose, the first column is 7 minus 2. If in the first matrix, the second row is 3, 0, in the transpose matrix, the second column will be 3, 0.
3, 0.
Right? Now, in the first chapter, in the first 4 lectures, we were studying systems of linear equations, and now I introduce matrices, and I want to show how you can write every system of linear equations in matrix form. Let me just start with an example. Suppose I have the equations 7x minus 3y equals 1. Minus 2x plus y equals 3. So this is 2 equations and 2 variables, inhomogeneous. Let me make this a 4 just to make it a little bit simpler. Yeah. So if I look at the coefficients of the equation 7 minus 3 minus 2, 4, I can write that as a matrix 7 minus 3 minus 2, 4. And let me write another matrix. It's really just a column vector, but a column vector is a matrix, of course. X times y. If I take this matrix times this and I multiply them, the number of columns equals the number of rows. I get a matrix where this is 7x minus 3y minus 2x plus 4y. And if I set this equal to the vector 1, 3, I have this matrix times the vector xy equals 1, 3. That's just another way of saying 7x minus 3y equals 1 minus 2x plus 4y equals 3. So I can rewrite any system of linear equations in matrix form. Let me look at another example. Suppose I have 3x plus 5y equals 2, 4x plus 7y equals minus 3. Let me show you a way to use matrices to solve this system of equations. If I write the matrix of coefficients of the equations, these are the coefficients of x and y on the left-hand side. I have 3, 5, 4, 7. So if I take this matrix and multiply it by the vector x, y, I'm going to get the vector, just matrix multiplication, 3x plus 5y, 4x plus 7y. And I want to find numbers x and y such that this vector equals 2 minus 3. Because this says exactly that 3x plus 5y equals 2. First equation, 4x plus 7y equals minus 3. the second equation. So let me call this matrix A. I want to find xy such that A times xy is 2 minus 3. Now, I already saw in the previous example that if A is the matrix 3, 5, 4, 7, and I let B be the matrix 7 minus 5 minus 4, 3, this is the inverse of A. So AB and BA equal the identity. So in this equation, let me multiply on the left by the matrix B. I would get BAXY equals B times 2 minus 3. But B times A is the identity. That's what I showed a few minutes ago. A and B are inverses of each other. B times A is the identity. So BA is just the identity. This is the identity times the vector XY. And the identity times anything is the anything. It doesn't change. This is XY. So XY is B times the vector 2 minus 3. What was B? 7 minus 5 minus 4, 3 times 2 minus 3. When I compute this, row into column multiplication, I get 14 plus 15 minus 8 minus 9. That's 29 minus 17. So according to this, by that x equal 29 and y equal minus 17, I have a solution of my system of equations. So let me check. 3x plus 5y is 3 times 29 plus 5 times minus 17. 3 times 29 is 87. 5 times 17 is 85. 87 minus 85 is 2. So the first equation is satisfied. And the second equation, 4x plus 7y equals minus 3. So that's what we have to check. So what is 4x plus 7y? X is 29. So this is 4 times 29 plus 7y, 7 times minus 17. 4 times 29 is 116. 7 times minus 17 is minus 119 is minus 3. So both of it checks. So here we actually use matrices to solve a system of equations. I wrote the matrix in, I used the coefficients of the equations to define the matrix A, and then I could translate the algebra problem into a matrix problem. But if I know that the matrix A has an inverse that I can calculate, then I can immediately solve the equations, which is a very convenient thing to be able to do. So one of my goals in this chapter is to explain how to solve every system of linear equations using matrices, and in particular, how to explain Gaussian elimination and carry it out using matrices. So let me just recapitulate what I've just been saying. And I'll write it now in its general form. Suppose we have m equations in n variables. A11 x1 up to A1n xn equals B1 down to AM1 x1 plus AMN xn equals B sub n. So from this system of equations, I forget the right-hand sides for the moment, and I let A be the m by n matrix of coefficients of the variables x1 up to xn. So here, as I go across the first row, the coefficients are A11, A12 up to A1n. If I were to go across the ith row, the coefficients would be AI1, AI2 up to AIN. All the way down to the last row, the mth row, this is AM1, AM2 up to AMN. So this is the matrix of coefficients. And then I have the vector of variables, x1 up to x sub n. Right? And then I have the numbers on the right-hand side, b1 down to bn. So I can rewrite this system. So this is the system rewritten in matrix form. It's A times the vector x1 up to xn is the vector b1 to b sub m. Any questions about this? Okay. Now, when we were talking about linear equations and Gaussian eliminations, the idea was to take a system of equations and simplify it to get an equivalent system of equations that had the same solutions, but maybe was easier to solve. And we saw three operations that we were allowed to do to a system of equations to get an equivalent system, which means a system of equations with exactly the same solutions as the original system. And the three operations were the following. We could interchange rows. We could multiply a row by a non-zero scalar, or we could add a multiple of one row to another. And the corresponding elementary operations on a matrix are the following. So this is a list of three elementary operations on a matrix. The first is to interchange any two rows. So for example, if I take the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, I could interchange the first and the second rows. This would be 4, 5, 6, 1, 2, 3, 7, 8, 9. I've interchanged the first and second rows, so I have a different matrix, but all I did was interchange rows. I can multiply any row by a non-zero scalar. So let's say from A, I could multiply row 3 by 7. So in this matrix, I haven't changed the first two rows, but I multiplied the last row by 7. I get 49, 56, 63. And the third operation I can do is I can add a multiple of one row to another. So let's say I add 2 times row 1 to row 3. So the first row isn't changing. The second row isn't changing. But I'm taking the third row, which is 7, 8, 9. I'm multiplying the first row by 2. If I multiply 1, 2, 3 by 2, I get 2, 4, 6. So if I add 2 times the first row to the third row, looks like I get 11, 12, 15.
Professor, sorry, could you just repeat the third rule there?
Okay, so you can add a multiple of one row to another. So I can take, for example, in this matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say I want to take 2 times the first row and add it to the third. So the first two rows don't change, 1, 2, 3, 4, 5, 6. If I take 2 times the first row, 2, 4, 6, and add it to the third row, 7, 8, 9, I get 9, it should be a 9, excuse me. I get 9, 12, 15. These are the 3 elementary row operations. So what this tells us is if we take a system of linear equations, apply some elementary operations to the equations, and then write it in matrix form. Alternatively, I could take my system of equations, write it in matrix form, carry out the corresponding operations on the rows of the matrix, and I end up with the same matrix in both cases. That is the crux of the matter.
Professor, what's the last row? The middle section of the matrix. The middle one.
4, 5, 6.
No, not that one. The one on top. Like,
Here,
no, down.
here.
No, not that one. Yeah, that one.
So
1,
in this,
2,
I'm
3.
multiplying the first row by 7. Sorry, I'm multiplying the third row by 7. So the
Oh.
first two rows, 1, 2, 3, 4, 5, 6, don't change. When I multiply 7, 8, 9 by 7, I get 49, 56, 63. I'm multiplying row 3 by 7.
Okay.
And we say matrices are called row equivalent if one can be obtained from the other by a sequence of elementary row operations.
What
So
did you
let's look at
multiply
some.
the
Yeah.
what did you multiply this one with? Is it 2 times?
Here,
Yeah, the one on the bottom.
multiply row 3 by
No,
7.
not that one. The one on the bottom. Yeah.
Here,
Yeah.
I took 2 times row 1 and added it to row 3. So 2 times row 1 is 1, 2, 3. If I multiply this row by 2, I get 2, 4, 6. Row 3 is 7, 8, 9. 7, 8, 9. If I add 2, 4, 6 to 7, 8, 9, I get 9, 12, 15.
Okay. Yes.
So let's look at some more examples. Suppose I take the matrix 1, 2, 3, 4, 5, 6. I can add -4 times the first row to the second row. Or equivalently, I can take the second row and subtract 4 times the first row. So 4 minus 4 is 0. 5 minus 8 is -3. 6 minus 12 is -6. So these two matrices are equivalent. So what I do here is I subtracted 4 times row 1 from row 3. And I got this. To get from here to here, I'm going to multiply row 2 by -1/3. So I'm not doing anything to the first row. If I multiply this by -1/3, I get 0, 1, 2. I could now add -2 times row 2 to row 1. So in this case, I'm not changing the second row, but I'm multiplying the second row by -2 and adding. 0 plus 1 is 1. -2 plus 2 is 0. -4 plus 6 is -1. So each of these 4 matrices is row equivalent to every other, because I got from one to the other by these elementary row operations. And that's the definition of matrix equivalence. Let's see. Yeah. Maybe I'm going to stop at this point because, well, no, I don't want to stop quite yet. There's just 1 or 2 more things I want to do. But it requires a lot of work on your part. That is, you have to do a lot of problems with matrices to begin to get a feel for it. Maybe for those of you who know Maple, I can show you how to do matrix calculations in Maple. So let me open up a Maple worksheet. So I want to share the screen with Maple. So the first question would be, how do we write a matrix in Maple? So there's an easy way and a hard way. And the easy way is on this menu on the left, you see matrix. See if I can make this bigger.
Recording in progress.
So let me open up matrix. And this says at the cursor, I can put in a matrix with a number of rows and columns. Let's just make it 2 by 2. So I can change this, but 2 by 2 And right here, I'm going to insert a matrix. And I can enter the coordinates just by typing in numbers and tabbing. So I'll just make this, I don't know, -5, 7, 11, 23. You don't have to be afraid of big numbers in Maple. Let me give this matrix a name. This is the matrix A. Let me insert another 2 by 2 matrix. B. Let's say this matrix is 13 minus 3 minus 17 minus 1. These are really just matrices I'm just making up at the moment. That's the matrix B. So if you want to add them, you can just write, I hope, let's see, A plus B. You want to subtract them. Matrix is case sensitive, so A minus B. Suppose I want to multiply a matrix by a scalar. Let's see how to do that. I can try it. Try 2 times A. Oh, sorry. I typed 28 times A, but that's okay. This is 28 times A. Suppose I wanted to do 5 times A minus 19 times B. Seems to work. How do I multiply A times B? So if you put a dot, it shouldn't work. Yes, because the command for multiplying matrices is actually the period. So that is A times B. What is B times A? And you notice AB and BA are completely different. Let's see. Can I square the matrix A? Oops. A squared. Oops. This is A squared. Seems to do it. Suppose I want to take A to the 21st power. You don't want to do this by hand. But that's what it is. You get these big numbers. So this is matrix addition and multiplication. This is the algebra of matrices. Yeah. Let's see. I wonder, can Maple give me the inverse? A raised to the power -1. That is supposed to be, that should be the inverse. So if I do A times A to the -1, I get the identity matrix. And if I do A to the power -1 times A, I also get the identity matrix. So you can do matrix calculations in Maple very easily. If you wanted a 2 by 3 matrix, or let's make it a 3 by 4 matrix. I change the number of rows to 3, change the number of columns to 4, and I put the cursor where I want to insert the matrix. And there it is. So I can enter coordinates. Just plugging in random numbers if you like. There's a 3x4 matrix. Let me give this a name. I'll call it R. Suppose I want to introduce a 3x3 no, I'll make it a 3x2 matrix. Call it S. So I want this to be a 2x3 matrix. So make this a 2 and make this a 3. And I'll put it in here. So insert matrix. I'll just make it easy. 1, 2, 3, 4, 5, 6. So that's the matrix S. So S is a 2x3, R is a 3x4. So I can multiply S times R. And if S is 2x3 and R is 3x4, this should be a 2x4 matrix. Oops, why didn't that happen? Here's R, here's S, S times R, there it is. I don't know what happened a moment ago. It's 2x4. Suppose I try to multiply R by S. It doesn't work because it's not defined. In R, the number of columns is 4. In S, the number of rows is 2. They're different. So it won't work. Just save this. Stop the share. Okay. All right. So that is all we're going to do today. Are there any questions before we end? There's homework on matrices, of course, and I have office hours scheduled or problem sessions at 7 o'clock Monday, Tuesday, and Wednesday of this week. So just log on when you need to. Okay,
Can
well,
you explain? Can
go
you
ahead.
explain again how you get the identity matrix?
I'm not sure what you mean by I got it. It's defined, the definition of the identity matrix.
I mean, how you get the inverse of a matrix?
Oh, computing inverses is hard. And Maple can do the calculation, and I will show you later how to compute the inverse. But it typically is very difficult. The only easy case is for a 2x2 matrix. So if A is the matrix A, B, C, D, there's associated to it a certain number called the determinant of A, which is AD minus BC. And so these are all theorems that I'll prove later, but A is invertible only if and only if the determinant of A is non-zero. And if you have the matrix A, if the determinant is non-zero, the inverse is 1 over the determinant of A. If the determinant of A is non-zero, I can divide by it, times the matrix D minus B minus CA. So this is a fairly simple formula for the determinant of a matrix. Now, In the example I had done earlier, A was the matrix 3, 5, 4, 7. So the determinant of A would be AD minus BC. 3 times 7 minus 4 times 5. That's 21 minus 20, which is 1, which is not 0. So I know this matrix has an inverse. And the inverse would be 1 over the determinant, but 1 over 1 is 1. Interchange A and D, change the signs of B and C. And that's the inverse. That's what I wrote down as the inverse. In general, it is computationally difficult to find the inverse of a matrix. One defines the determinant of any square matrix, not just 2 by 2 matrices. And the matrix has an inverse if and only if the determinant is different from 0. But the calculation is very hard. I mean, just because it takes a long time and you'll make a mistake. So it's not too hard. It's hard, but not too hard for a 3 by 3 matrix. Beyond that, you want to use a computer to calculate the determinant. Right? That's a good question. Anything else?
Professor, you said there was homework on matrices. Is that on Blackboard yet, or will that be posted later?
I'll check I'll check in a minute, and if it's not there, I'll post it. Oh, sorry.
Okay,
excuse me.
thank you.
No, I'll check. If it's not there, I will have it posted very quickly.
Thank you.
Any other questions? No. Okay. Next class is Wednesday morning. Bye all.